LiDAR-Inertial Odometry, or LIO, is widely used in autonomous navigation, but deploying it on small, low-power systems is challenging. Processing dense point clouds requires significant computational power, causing bottlenecks and memory issues. This makes real-time execution difficult on embedded platforms. Conventional LIO faces high computational overhead and drift from biased downsampling, making real-time deployment on embedded systems impractical. To solve this, we introduce QLIO, a multi-processor, quantized LIO framework that reduces computation and bandwidth while maintaining localization accuracy. Instead of processing full LiDAR scans, QLIO uses a coprocessor to pre-process and compress data before sending only essential features to the host processor. When a LiDAR scan arrives, the coprocessor requests the latest pose from the host processor, which integrates IMU data to estimate motion. The LiDAR points are transformed into the global frame, compressed, and sent back to the host processor for state estimation and system updates. We quantize points, residual vectors, and points to planes residual. Using RQ vectors for hash bucket classification, we perform 3D adaptive resampling to achieve sparser and more uniform point distribution. Crucially, we implemented group compression by bundling resampled points and residuals Z into compact bit streams through RQ vector-guided clustering, significantly reducing data volume. This compressed package was then transmitted to the host processor for quantization-based estimation. We evaluated QLIO on the MCD-NTU dataset, collected using an ATV at NTU equipped with a Livox Mid-70 and a 128-line Ouster LiDAR. Compared to fast LIO, QLIO eliminates the directional bias introduced by conventional downsampling methods while maintaining stable optimization. This allows us to reduce data volume while preserving accuracy, making real-time deployment more feasible. We systematically studied the effect of different quantization bit allocations. Results showed that using 1-bit residual components led to system failure due to precision loss, especially on MID and OS platforms. Increasing residual component bits improved stability, with the best trade-off found at 4-bit quantization, reducing data from 32-bit floats while maintaining accuracy. Our approach achieved 1.5 KB per frame bandwidth, making it compatible with low-power communication protocols like UART and SPI. RQRS optimizes LiDAR quantization, achieving 5.84 to 14.84 bits measurement with minimal precision loss. It compresses points via 3-bit residual vectors, reducing bandwidth to 1.5 KB per frame on MCD D10, enabling efficient SLAM on edge devices. QLIO enables real-time LIO on edge devices via multiprocessor quantization and adaptive resampling, achieving 15.1 times bandwidth compression while preserving accuracy. Unlike 2D visual methods, it introduces 3D point-to-plane quantization and a LiDAR-specific map estimator. For more details, please refer to our paper. Thank you for watching.